Let's continue with our lecture on mathematical methods. We have been looking at the complex analysis. We have seen the Cauchy-Riemann condition and harmonic functions. Now we have studied how to solve Laplacian in a Cartesian coordinate system. So idea there is very simple. Use the eigenfunctions of the two differential operators which come in the x and y variable. Now let us extend this to polar coordinate. In the polar coordinate, the differential operator or the Laplacian operator looks slightly differently. Some parts are similar and some parts are dissimilar. So let's have a look at how to solve a Laplacian in the plane polar coordinate. You have a two variable r and theta, and then let's see how we use the idea of eigenfunctions to solve this Laplace equation. So here we are looking at the Laplacian in the polar coordinate. This is a part of course PH3103 at IISER Calcutta. Laplacian in the plane polar coordinate. We have seen how to solve a Laplacian in a Cartesian coordinate system. We have a simple differential operator there, del square phi by del x square plus del square phi by del y square is equal to 0. The both this differential operator of the same form, that d square by dx square, and we know that the eigenvector or eigenfunctions of this differential operator is e power plus or minus ix or e power plus or minus x, depending on the constants. These constants may be coming from the separation of variable or coming from the physics itself. So the solution in general could be linear combination of these functions. So often we use sine and cos, or hyperbolic sine and cos. That is because they are sometime suitable to satisfy certain boundary condition given to us. Laplacian in the plane polar coordinate r theta is given by 1 by r del by del r into del phi by del r plus 1 by r square into del square phi by del theta square is equal to 0. So one immediate observation here is that the del square phi by del theta square is very similar to del square what we have seen in the Cartesian coordinate system. So immediately we know what kind of a solution we can propose. In this case, eigenfunctions can be e power plus or minus ix or e power plus or minus x, or a suitable combination of them. And then we can go ahead and solve in a very similar procedure which we have already used. So let me deviate a bit. My choice of combination is a linear combination of e power plus or minus I omega x, which I write as a cn sine omega theta plus theta naught, where theta naught is a constant phase. Why it is so? Because sine is more familiar, it brings in the familiarity, and this constant phase, if we expand that, we get sine theta plus sine theta naught plus cos theta into cos theta naught. This is writing as a linear combination of solution sine theta and cos theta. So this is general enough, while it gives a compact equation what we are looking at. Going back to our Laplacian, now we have to propose a solution. The proposed solution phi of r theta is equal to sum n going to 1 to infinity c of n. The c of n will be now function of r, because though we know what is the eigenfunction for this, we are somewhat unfamiliar with this function, so we believe it and then solve it later. So Cn of r we need to solve. The solution is sine omega n theta plus theta naught. Now we substitute this back into a differential equation, and then we obtain the condition 1 by r d by dr r into d by dr plus 1 by r square d square by d theta square, and now we apply our series solution of sine omega n onto this. Now we expand this. Sine is eigenfunction for this operator, so this will just comes out as it is with the eigenvalue omega square n. R term remains same, so resulting differential equation is 1 by r d by dr into r into dcn by dr minus omega n square r square cn sine omega n theta plus theta naught. Here we have assumed that the cn is a function of r, and hence we get a differential equation in terms of the cn of r. Now, since the sine omega n are linearly independent for values of omega n, so in order to satisfy this equation, each term or term by term, the coefficient have to be 0. So this implies 1 by r d by dr, r into cn by dr minus omega square by r square cn is equal to 0 for each omega n. Now we can write this as a ODE instead of a partial differential equation. The resulting ODE, by after making them suitable adjustment, is that r into d by dr into r into dcn by dr minus omega square cn is equal to 0. Now our goal is to solve this differential equation and obtain a solution for the Cn of r. Let us look at the differential equation and what could be this differential equation. The differential operator here is what we need to focus on. They definitely don't have sine or cos as their eigenfunction, so we have to look for some other solution. Why not check for r to the power n? So let's propose that the Cn is r power n. Interestingly, when we first differentiate this, r into c drn by dr become just n times r to the power n. So it acts as a eigenfunction for the first order term, but that's not sufficient. We have a second order differential equation. Let's apply again r into dr. Then we see that what comes out is a n square r to the power n. So this clearly shows that the r to the power n is a eigenfunction for this differential operator, and the n square is a eigenvalue. So this differential operator is called the Euler differential operator. L is equal to r dr into r into d by dr. So this has an eigenfunction r to the power plus or minus n, and the eigenvalue as a n square. Now basically we have solved the problem. We know the eigenfunction of the both differential operator. All we need to do is put all together and then solve it. Now we can easily solve the ODE r into d by dr into r into dcn by dr minus omega square cn is equal to 0. So once we substitute r to the power n, we get omega square is equal to n square, or omega is equal to plus or minus n. So finally, the complete solution for the potential phi can be given as a combination of all these functions. One is a sine and cos, another is a r to the power plus n and r to the power minus omega n. So we have a phi of x is equal to n going to 1 to infinity a n r to the power omega n sine omega n theta minus theta naught. This include both sine and cos. Note that we have already shown that because of this phase, we have incorporated both sine and cos solution. Now other linearly independent solution corresponds to omega is equal to minus omega n, that is n going from 1 to infinity n r to the power minus omega n sine omega n theta minus theta naught. This is the general solution in terms of the both all the possible combinations we have taken. Since it is a very general solution, and depending on the physical cases, one may have to take the certain part of the equation to be 0. One of the problem here comes is that some of the terms might blow up. For example, r to the plus n blows up at infinity, because r to the power n would blow up as r going to infinity. The same way, r to the power minus n, 1 by r to the power n, goes to infinity when r goes to 0. So physically, we don't want the solution which blows up. This is a merely common sense, but one has to be cautious each time when apply what is physically allowed and what is physically not allowed. But in this case, option is rather trivial. The solution blowing up in the particular domain is not what physically we are looking for. Let's say that when we have a region from minus infinity to plus infinity, it's rather a complete complicated domain. One may restrict their domain to a specific region. Suppose we have a 0 in our domain. Let's say you are using domain in which r is equal to 0 also incorporated. Then we cannot use the series with the negative power. That means your solution have to be only in terms of n is equal to 1 going to infinity, a to the power n, r to the power plus omega n, sine omega theta minus theta naught, because r to the power minus omega n blows up and we have to ignore that solution. On the other hand, if we have an infinity in our domain, in such a case, we cannot use r to the power plus n. Then we have to use the series which involves only r to the power minus n, and that is this term only. The solution in the such case would be r phi of r theta is equal to n going to 1 to infinity b to the power n r to the power minus omega n sine omega n theta minus theta naught. Here the solution would go to 0 as r tending to infinity. So this is, one has to be careful. One cannot have a clean solution when both 0 and infinity are there. Somehow one have to restrict yourself to study the region close to 0 or region close to infinity, so that these Laplace equation can be expressed in terms of the series solution. Now that we have seen how to solve a Laplacian in the polar coordinate, let's look for some problem to solve. So we already have seen a problem from electrostatic. Let's relook at the problem, because it's a fairly rich problem in terms of physics, and we have already have a lot of confusion about this. This is about the two parallel plates kept at the angle, and we are looking for the solution inside the plate, metallic plate. The metallic plate goes all the way till infinity. We said that the potential is maintained 0 on the metallic plate. Even if we keep at some constant potential, we can easily subtract that and solve for the 0 potential, and then we can add the constant value. We can use the polar coordinate, and in this case we know that we can write down the solution in terms of phi of r theta is equal to n going from 1 to infinity, n r to the power omega n sine omega n theta plus n going to 1 to infinity, a to the power n r to the power minus omega n sine omega n theta. Here omega n, we have said that n pi by theta naught, such that it satisfies the boundary condition of 0 potential on these both metallic plate, that is theta is equal to 0 and theta is equal to theta naught. Now clearly see that there is a problem here. We have both 0 and infinity in our domain. So in principle, we cannot throw out any of these terms.